What we're going to talk about today is a continuation of the last 3 days. The if-then statements that we've been talking about, the biconditionals, the definitions, those things had to be introduced so that we could get to this, okay? Because the deductive reasoning that we're going to talk about today incorporates us being able to read one or two if-then statements and kind of stitch them together to create other facts, okay? Deductive reasoning is something in which most of our mathematics is developed from, and it's pretty much the logic that you use probably 95% of the time in everyday life, regardless of mathematical relationships or not, okay? There's a couple different types of reasoning. One we call inductive reasoning. Okay, so if I say like 2, 4, 6, 8, what's the next number I'm going to say? 10 and then 12, right? So you do patterns, right? Okay. If I say, triangle, square, then I say pentagon, and then hexagon, heptagon, the next one's going to be octagon, right? I've been taking figures and adding one side to them and naming them, okay? So you can generate patterns and understand you can predict what's going to be next using patterns, and that's called inductive reasoning, okay? Inductive reasoning. A lot of your algebra is actually defined and developed, proven using inductive reasoning, but a lot of mathematics overall, we use deductive reasoning, okay? We will talk about that pattern stuff later on, and how we can use induction, which is the way we talk about inductive reasoning, to do some types of problems later on, but most of the time we're going to use deduction, okay? What deductive reasoning is, and this is kind of, you're going to say some of this stuff, Mr. Fay, is obvious. It's almost trivial or just common sense, okay? But we need to make sure we understand it, because when we start applying it in our mathematics to things that are properties and rules that govern mathematics, it might not be 100% kind of common sense because of the items and the content that we're using it with, okay? So deductive reasoning, sometimes called logical reasoning, other textbooks call it logical reasoning, is the process of reasoning logically from given statements or facts to a conclusion. Now, I don't think that's a great definition, so kind of pull that apart with those other two bullets, okay? Basically what it says is that you are going to be provided true statements, okay? And that's what we say given. If anybody says that's given, okay, then that's kind of, you've had that conversation with people in the past, and they say something, yeah, that's given. I mean, so that means that's a fact. That is something that we've agreed upon to be true, okay? So whenever they say that something is given, that's the idea. It's agreed upon to be true. Or other facts to a conclusion. So using given statements that we've agreed to be true or facts together to make a conclusion. Okay? If you think about that, that's how law is done. That's how we operate in a courtroom. Okay? That's how Congress operates. Okay? We take facts that we know to be true and we stitch them together to maybe prove somebody innocent or to prove somebody guilty in the court of law, right? Okay? There are times, but it's few and far in between, that we use patterns to maybe convict somebody of something. Okay? We need to be able to provide facts and properties to convict somebody or to make a conclusion about somebody. Okay? It's deductive reasoning is what you use to make decisions on a regular basis about how you're going to live and how you're going to interact with the environment and the people around you, okay? So it's the idea of making a conclusion based on already known facts, such as definitions, postulates, and or theorems. That's how we're going to do it in math. Those are the facts, the definitions, or the given statements that we're going to be using are definitions. So we're going to need to know our definitions. They're postulates, so we're going to need to know those true statements that we've agreed upon being true. And then other theorems, which are things that we can prove to be true, but they are true as well. So when you use these categories of statements, that are governing our geometry, and we're going to kind of stitch them together, okay, and use them to make conclusions about things, okay? The most simplest way of thinking about deductive reasoning is using things we already know to be true to make a conclusion, to make an argument, okay? For instance, if you're going to make an argument, you guys probably maybe argue with one another, maybe argue with your parents, stuff like that. If you're going to try to prove your argument true, you're going to want to try to use facts to do that, aren't you? Okay? And probably use facts that you and your parents agreed that they are indeed facts to begin with. Okay? Otherwise, your conclusion that you're trying to argue with them probably isn't going to sit well with them. It's probably not going to be valid. They're not going to agree with it. Okay? So, that's deductive reasoning. Within deductive reasoning, there are two main laws. One of those is called the law of detachment. Okay? And they've got weird names. Okay? And their detachment means to, if I detach something, I pull it apart, right? Okay? That's kind of what is going on here when we go through this process. And I don't think that the if-then statement here in the law is a great one, but this is how 99.9% of your textbooks are going to present the law of detachment. Okay? So I'll let you write it down, but then we'll pull it apart and kind of explain really what it means. It says, if the hypothesis of a true conditional is true. And I think that's kind of weird. If a hypothesis of a true conditional is true, we'll talk about what that means here in a moment, then the conclusion is true. If the hypothesis of a true conclusion is true, then if the hypothesis of a true conditional is true, then the conclusion is true. As you write that stuff down, I'm going to write an example here that I think will help us make sense of that phrase. All right. So, reading that says, if the hypothesis of a true conditional is true. What that is saying, guys, is if we have a mathematical statement, okay, and to be honest, it doesn't have to be a mathematical statement. It could be any if-then statement, but we know it to be true. So I want to use a mathematical thing that we've done, okay? So we have this red statement that says, if two angles form a linear pair, okay, then the sum is 180 degrees, or the sum of the measures is 180 degrees. That's a fact that we talked about in Chapter 1. That's the linear pair postulate, okay? It's an if-then statement, okay? So what they mean by if the hypothesis of a true conditional is true, that statement means if you've got a true conditional, and then in front of you, okay, you have got a situation like we got there in example 1 that is true and is matching the hypothesis of the red statement. Would you guys agree that angle 1 and angle 2 there in front of me, in example 1 on my specific problem, is matching the hypothesis given in that red statement? It is, correct? Okay. 1 and 2, and now we have to, and this is where we lose some people, and we got to make sure that we don't lose them. But in order to be able to say, yes, we've got matching ideas here, is that we have to know what a linear pair is, right? We have to know that vocabulary. Linear pair is a pair of adjacent angles whose non-common sides form a straight line. Okay? So that's what's going on in front of us. We've got angle 1 and 2. They're forming a linear pair. By definition, they're forming a linear pair. So we've got right now in front of us a hypothesis that is matching the hypothesis of a true conditional statement. So the rest of that statement, the law of detachment, says if that's occurring, if this particular problem here matches that statement, then you can, with this property or this particular situation, make that conclusion. You can conclude then that your specific angles 1 and 2 should add up to 180 degrees. Does that make sense? My hope is that that's like obvious, right? Okay? But eventually, some of the things that we work with, it's maybe not so obvious, okay? And you heard me talk about this last couple of days. We're going to think about the way we think, okay? And this is the idea that allows us to make true arguments about something, okay? A lot of lawyers end up doing their undergrad work within mathematics and or English, okay? Because if you can understand those systems and how you operate logically within them, you're probably going to be a pretty good lawyer, okay? Because you can follow rules, you can learn rules, you can understand how to stitch 2 or 3 laws together to create a new one, okay? You understand how to violate them and how to not violate them, that kind of stuff, okay? And they understand this principle very well. The second example, and this is the thing, okay? The second example, does that angle 1 and angle 2, does that match the red hypothesis that says 2 angles form a linear pair? Are angles 1 and 2 a linear pair? Do their non-common sides form a straight line? Well, all their sides are non-common, right? Okay? So we're not forming a straight line there. Those angles 1 and 2 are not like the angles 1 and 2 in example 1. So 1 and 2 on the right are not matching the hypothesis. So those are not a linear pair. So if they don't match, then I can't make a conclusion based off of that red statement about angles 1 and 2 and that example on the right. Does that make sense, everybody? Now, here's where you need to be cautious. Because if it doesn't match, people say, oh, 1 and 2, if it doesn't match to that statement, that 2 angles form a linear pair, then they want to say, then it doesn't match to this conclusion. So what they want to argue then is that angle 1 and angle 2 are then not 180 degrees. And that would be false. You don't want to do that, okay? Because if I told you angle 1 might be 140 and angle 2 might be 40, they would still add up to 180, right? So just because they're not a linear pair doesn't mean they're not 180. It just means because they're not a linear pair, right now I can't use that fact to say that they're 180. They might indeed be 180, but I don't want to make that conclusion that they're not. Does that make sense? Okay? So, when we say that we cannot make a conclusion about something because the idea does not match the hypothesis, it does not then allow you to make a complete opposite statement about those things that is in relationship to the conclusion. So if I were to, let's say, if I say you're not an A student, okay, not an A student, does that automatically make you the opposite and make you an F student? No, you could be a B, a C, or a D, right? Okay? So just because I can't make that conclusion about you does not open the door for you to say the complete opposite, okay? So just be very, very careful with that as we move on through the year. If I say I cannot tell you 2 angles are congruent, it doesn't mean the angles aren't congruent. It just means I can't tell you that. I don't have enough information. Does that make sense? Okay. So as it says these bullets, it says in order to use the law, you must first identify the hypothesis of the given true conditional. The second statement that's going to be provided. So that second statement, guys, throughout the year, obviously in this section it's going to be a defined second statement. But throughout the year it's going to eventually be, each homework question. Okay? And you might have to use this property, this law several different times in each homework question. Okay? Because you're going to have to look at certain things in that homework question. Say, okay, do these two things that I'm working with, these two angles, do they form a linear pair? And if they do, okay, then I can make this conclusion about them being a linear pair. And then I can look at my picture and say, okay, well, are these two angles vertical? And then if they do, I can make the conclusion that I can make about all vertical angles. Does that make sense? So the way that we use and apply properties is going to be using what we call the law of detachment. So here's another example. And these examples, with trying to kind of get us to use these logical practices, try to maybe kind of make the statements kind of elementary first. Take all mathematical aspect out of it. Okay? So I'm going to give you this given statement. So we're going to all accept that this given statement is a true fact. It says if a student gets an A on the final exam, then the student will pass the course. You get an A on the final exam, then the student will pass the course. So what we do is we highlight our hypothesis. That's our hypothesis. Okay? We want to see if our second statement that's given below matches that. Okay? Now, it doesn't have to be verbatim. Okay? Or, do you guys know what verbatim means? Like word for word. Okay? Like a cut and paste type thing. It doesn't have to be that way. Okay? But it has to be idea for idea. Okay? Meaning that the one I highlighted can't have any extra components that the one in the second statement has, or vice versa. Okay? But would you agree that Felicia is potentially probably a student? So there's a one-to-one thing. Okay? And it doesn't have to say a student. You just put that person's name. She gets an A on her history final exam. Now, the one I've got highlighted doesn't say it's got to be a history final exam. It just says it's got to say final exam, right? But would you agree that those two ideas match? Okay? So if those two ideas match, then you can make an argument about Felicia. What's the argument you're going to make about Felicia? She passed the course. Okay? That's hopefully to you common sense. Okay? And that you realize that you've done this before. If you show up to school late, then you are tardy, right? And if you show up late, then what happens? You get tardy, right? Does that make sense? We do this all the time. Okay? If you come to Mr. Fay and ask to go to the bathroom, then he says, yes, go to the bathroom. Okay? And we ask all the time, right? And then you go. Okay? So everything that we do in life usually has an aspect of the law of detachment. Okay? However, there are some things that don't. Okay? Let me get down to this example here. It says if two angles are adjacent, then they share a common vertex. If two angles are adjacent, then they share a common vertex. That's absolutely true. Okay? Absolutely true. Okay, the reason that's true is that comes from the definition, right? Adjacency has to share a common vertex, but they have other components. Now I want to highlight my hypothesis. And I want to highlight my second statement that they provide me. And here's the idea that we've got to be careful with in recognizing whether those match or not. Okay? It says two angles are adjacent. So when we have two angles that are adjacent, that means they share a common vertex. They have no points in common, interior points in common, and they have a common ray. So there's three aspects, three components to adjacency, right? When I look at that bottom statement, angle 1 and angle 2 share a common vertex. Does that say the same thing that two angles being adjacent says? No. Being adjacent says three things. That statement only says one of those three things. So adjacency is more detailed. It's more convoluted than what a common vertex says. Okay? Meaning then These two things do not match. Okay? They do not match. Okay? So if there's not a match, then all you do is say there's no conclusion. I cannot say anything more about angle 1 and angle 2 other than the fact that they share a common vertex, because that's the information provided in the statement. I cannot go on any further. Does that make sense? Okay? Now, you've done this a lot in algebra. Okay? So I want to make an algebraic argument here. You guys remember if I have like something like a to the third, b squared raised to the fourth, you guys remember how to rewrite that or simplify that? You guys remember rewriting this as a to the third times 4, b to the second times 4, and that turns into a to the 12th, b to the 8th. You guys remember doing that? Okay. Or a lot of people just kind of draw the picture like this and say, I'm going to take that 4, I'm going to distribute it to my 3 and my 2, and just multiply those exponents. Okay. So when we call that a power to a power in algebra. When that's the case, you just multiply the powers. Okay. Now, here's the idea. This last year in your laws of exponents was probably presented in a table of some fashion that was presented in your textbook. But we can do it this way. We can write as if a, and I'm going to just say m to the m, b to the n, raised to the c, then you're going to rewrite that as a to the MC, B to the NC. And that's exactly what I've got going on right here, right? Okay? That is an algebraic property. That's an algebraic fact. And then lastly, if you learned that, then last year, in your homework, you were given questions like this. 3 to the third, x to the fifth, raised to the fourth. And you're trying to decide, well, what do I do with that? Well, this is your true conditional statement. Okay? And this matches this hypothesis, does it not? And because they match, then you can do what is stated right here. You can take the m and the c, which would be that, and you can multiply them together and use that as the exponent for your base of 3. You can take the 5 and the 4 and multiply them together, and you can use that as the exponent for your base. You guys remember doing that kind of stuff? Okay, now you probably didn't write them as if-then statements and apply it that way, but that's how math works. That's how we decide what to do and when to do it with our operations. Okay, because they're defined somewhere in a rule for us, and then we, with specific problems, see, well, which rule does that match to? Which hypothesis does this phrase match to? And then once we find our match, we then jump to the conclusion that is being identified in that conditional statement that matched. Does that make sense? Anybody? Okay. So we've done this before. We may not think about doing it, but it is something that we have done on a consistent basis. In this class, we're going to have to think about doing that. We're going to have to know that that is a procedure and a process of thought. Okay? This one here is another example. It says if a ray divides an angle into two congruent angles, then the ray is an angle bisector. So here's my hypothesis. And now I'm going to look at the yellow statement here. There's my second statement. So maybe this is presented to me in a homework question, in maybe the directions, or maybe it's provided to me in a picture. Maybe the picture kind of looks like this, that I get that statement from. Maybe I've got, so there's R and S, there's A, there's B, okay? And maybe I've got that right there. Maybe that's the picture. Maybe there's some algebra attached to it so I can set up an equation or something like that. But if I look at that information right there, that is matching, whether I look at it in words or I look at it in the picture, it is matching that right there, isn't it? RS in that red picture is providing me two congruent angles. It's taking a bigger angle, ARB, and it's providing me two congruent angles. Then I can make the argument about that ray, because this matches that hypothesis, I can make an argument that ray RS is an angle bisector. Okay? Is that all right with everybody? Here's why this is important. What if I do this? Now you don't know, right? Now you do. I took the notation out that tells you that ARS and SRB, those angles, I don't know if they're congruent or not. So because I don't have that notation in there, can I say angle RS is a bisector? I cannot say it, right? Because it doesn't match that blue statement. But if I can't say RS is an angle bisector, do I want to say that it's not an angle bisector? I don't want to do that, okay? When I make a conclusion about something, okay, if I can't validate a conclusion, I can't come up with a firm conclusion, and I just say, I don't know enough information to go beyond this, okay? So I don't know, maybe ray RS is an angle bisector right now, maybe it's not. I don't want to make that argument. Does that make sense? Okay? Whenever you cannot make a conclusion, you do not want to then assume something else. You just want to say, don't have a conclusion. Okay? The law of syllogism. We use this all the time. Okay? Use this principle all the time in everything that we do. But now we're going to try to think about situations where maybe we've used this. Okay? So the second law allows us to state a conclusion from two true conditional statements when the conclusion of one statement is the hypothesis of the other statement. Okay? What's going to happen with this structure is that they're going to give you two if-then statements. They will always have to give you two if-then statements. And those two if-then statements are going to be true. Okay? They're going to be true. The law of syllogism allows you to take those, if they have the correct formatting, and you can stitch them together to create a third if-then statement that is new and different, but at the same time true, without you even having to think about whether it's true, because the first two that it came from were true. You guys remember that when we started definitions, we started with points, lines, and planes. Points, lines, and planes, and we said those were undefined terms. We don't have a really good definition for them, but those are our starting blocks. We can understand them intuitively, but those are our starting blocks for geometry. Then we put those together, and we can come up with new things. Okay, put some points together on a line, we get collinear points. We got a new definition. Okay, new vocabulary word. Kind of start putting things together, maybe we develop rays. Maybe we put some things together, we develop an angle. We get new vocabulary words. So we stitch smaller things together and create bigger concepts. Does that make sense? So in this class, I'm going to give you several statements, several properties that are true, and then you can stitch them together to come up with something new that is also true. And then maybe take that one and stitch it together with something else and get something else that's true. Okay? So this is the law of syllogism. This is how we start with a small set of facts and stitch them together to get ultimately a very large set of facts. And they're all true. Okay? The symbolism here is kind of weird. It says if P implies Q. Okay? So if P implies Q is true. So you got a first if-then statement that is true. And you got a second one. Q implies R is true. The key thing here is understand that they're using the same Q. Okay? So the Q in that first P implies Q is the conclusion. The conclusion of that first if-then. The Q in the second line is the same statement, but now it's starting to have the hypothesis in our second statement. And this says Q implies R is true. Then what we can do is you kind of visualize merging those two lines together. Kind of like this, if I have P implies Q, but Q implies R, if I were to take these and merge them together, I get something like that, right? So it says P to Q, but Q goes to R. Why not just make the jump straight from P to R? And that's the argument here. We can do that. And what happens then when you do that, P implies R is a true statement. So look at the example over there. It says if it is July, then you are on summer vacation. Okay, we're going to say that's a true statement. Here's the second one. It says if you are on summer vacation, then you work in a smoothie shop. We're going to assume that that's true. We have right here the conclusion of one statement. So that's the Q right here. Matching up then to the hypothesis of a second statement. That's the Q right here. Does that make sense, everybody? Because those two things match, you can create a new statement, and the new statement is going to be that thing right there followed by that thing. Okay? And you see then there it says you conclude, if it is July, then you work at a smoothie shop. And we can be guaranteed then that that is true. Okay? Is that all right with everybody? So we do then just an example where we're talking non-mathematical things. Let's say if you get in a fight, then you get Saturday school. If you get Saturday school, then you spend the morning with Mr. Fay. I do Saturday schools. Okay? So let's say that is happening. Would you guys agree that if I logically think about this, if you get in a fight, then you get Saturday school. If you get Saturday school, then you are spending the morning with Mr. Fay. You could make a third statement that says, if you get in a fight, then you're going to spend the morning with Mr. Fay. That's new, right? That's a new statement. It's different than the ifs and thens that we started with, and it's going to absolutely be true because we use those first two there to stitch together and come up with something new. Okay? So as we work through and we start getting, guys, new, we're going to call them theorems. Okay? New theorems in the textbook. Okay? Theorems are usually developed by stitching together postulates and definitions. We stitch 2 or 3 or 4 postulates and 2 or 3 definitions together, we'll get a theorem. And then we'll stitch a theorem with another theorem, and we'll get a third theorem. Okay? And we do that throughout the year, and these theorems are going to present properties for us. Okay? A theorem, for instance, might say, in an isosceles triangle, the base angles are congruent. Okay? That's a theorem that we're going to use all year long. But that's developed through an understanding of other theorems and stitching together other theorems. And that's what we do when we prove a statement true. We try to stitch things together. If I'm a prosecutor or a defendant in a courtroom, and I'm trying to maybe prove somebody guilty, say I'm a prosecutor, prove somebody guilty, I'm going to try to stitch together as many possible facts as going to persuade the jury to believe that this person's guilty, right? If I just go to the courtroom, I'm a prosecutor, and I say, he's just a bad guy. Is the jury going to say, yeah, he's guilty, he did it? Because my opinion of him being a bad guy. But if I could say, Drake has had a habit of doing this type of stuff. He's got a rap sheet that's, a mile long. I can put him at that vicinity during the time of the crime, that kind of thing. I've got these eyewitnesses, okay? And I can stitch all those things together to develop a case. Do I have a better chance of proving him guilty? Does that make sense? Okay, or if I'm a defendant, if Drake's my client and I'm defending him and I just say, he didn't do it, he's nice, he's a good guy, he's paying me. Okay? Are they going to believe me? Probably not, right? You got to put together a case. You got to put together a fluid statement Okay, an argument that has no gaps in it. And the process of doing that is using the law of detachment and the law of syllogism. Okay. Now, some of these are a little bit, like I said, they eliminate a little bit of our mathematics. Okay, and we got one talking about gymnastics and ballet and all that kind of stuff. But if I read this, and this is what I want us to realize, it says if a figure is a square, then the figure is a rectangle. If a figure is a rectangle, then the figure has four sides. If I read this, and we're going to assume that these are given. You ever had a conversation with somebody, you're arguing with everybody, or somebody, and then they say, well, yeah, that's given. We agree that's true, right? Whenever you say, well, that's a given fact, that means we're assuming that we already know, as both parties, that it's true. So this is given, okay? If a figure is a square, then the figure is a rectangle. If I look at that conclusion, does that conclusion match that hypothesis? Does that make sense to everybody? And it doesn't have to be in that order. It doesn't have to be the first conclusion matches the second hypothesis. It could be the second conclusion matches the first hypothesis. Okay, so we'll talk about that in an example here in a moment. But those match, right? We agree the yellow phrases match. If the yellow phrases match, then everything that I haven't highlighted put together would generate my third if-then statement that I know to be true. If a figure is a square, then the figure has four sides. And what's nice about this, guys, is we talked about how if we have an if-then statement, we're looking for counterexamples, right? Looking for things that would make it false. Well, if I know I used two if-then statements that were true, and a hypothesis and the conclusion of those two things matched up, this third statement that I make is 100% absolutely true. No counterexamples exist, and I don't have to spend time trying to find them. I know that they won't. Okay? When I look at this bottom one, I'm going to split this apart real quick to prove my point. So when statements are provided to us, guys, as given statements, okay, what we're thinking eventually is that these given statements are our mathematical properties. They are, if we look to the back of the book, they're all our definitions, they're all our theorems, our postulates, and they are usually in the back of the book categorized alphabetically as definitions, or as we see them throughout the textbook in chronological order. But here, when we're looking at any statements, we don't know if this one came first or if it came second. Does that make sense? Okay? So because they're both true, then it doesn't matter which one came first or second. So when somebody's asking, can you take these two true statements and come up with a third phrase that is also true, you're going to highlight that conclusion and that hypothesis, and you're going to see if they match. Okay? Now, here's the idea. They have to match idea for idea. Okay? Maybe people that are flexible do ballet. Maybe people that do ballet are flexible. But does flexibility mean the same thing as ballet? Are those a match? Yes or no? You guys can shake heads. Yes, no, no. Okay, so no. So they do not match. So in that order, these two things do not produce a third phrase. That's not enough to say that I don't have a third phrase. What I then have to do is reorder them this way. Because now I'm going to match that new conclusion with that new hypothesis. Does that make sense? You see how now we're comparing two different things? Okay. Now flexibility, does that mean gymnastics? And does gymnastics mean flexibility? They don't match, right? Okay. So I want you to make sure that if you're going to say that you cannot create a third statement, that you look at those statements in both orders. Okay? For the mere fact that we might have something that looks like this, we might say, if you do ballet, then you do gymnastics. And then let's say, if you do gymnastics, I want to do it this way. There we go. If you do gymnastics, then you are flexible. All right, so if I look at them this way, look at these two statements this way, and I compare that one, that conclusion, with that hypothesis, do they match? Is being flexible and ballet the same thing? No, right? Okay. So if I were to erroneously say there's no third statement I can make here, a person that understands what we're doing is going to put this one after that one, and now, looking at that one, you do gymnastics, do those match? Now I can see that there is indeed a third phrase that says if you do ballet, then you are flexible. And because we agreed that the first two were true, that would have to be true. Does that make sense? So you always have to be able to do, you have to understand that the order of your two given statements, they're independent, meaning that they can flip around. Okay? What they like to do, this will be the last one we do, combine these two laws. Okay? Now I don't know if I pronounce these things right or not, but if you live in Accra, then you live in Ghana. Okay? So a map over here shows you where Ghana is, shows you where Accra is. That would be a true fact. Okay? If you live in Ghana, then you live in Africa. Well, that's a fact as well. So we have two true if-then statements, right? Would you guys agree that you live in Ghana, that's a conclusion, doesn't match that hypothesis? So what I can do then is I can create a third statement that says that yellow. If you live in Accra, then you live in Africa, correct? So you generate this third statement. That's the law of syllogism. Okay, so I got this third if-then statement, the new if-then statement, and now it says this lady, Asia, lives in Accra. Well, does that match up with the yellow hypothesis? If Asia lives in Accra, what new statement can you make, or what conclusion can you make then about her? She lives in Accra, she lives in Africa, right? Okay. So what happens here is that we've got three phrases here, two if-thens and a third statement, and we're using the law of detachment and the law of syllogism together to kind of move along the line and make a valid conclusion about this person. What's going to happen in this class is that we're going to take 3, 4, 5, 6 statements that are mathematical, okay, geometric if-then statements, and we're going to stitch them together to kind of move along the line, move along the road that allows me to get to a final conclusion about something that I know is absolutely true, because everything that I stitched together was done so using the law of detachment, law of syllogism, using already true statements. Okay? And that will make a whole lot more sense when we start doing examples, doing some initial proofs, but we have to understand what's allowing us to stitch those things together. Okay? Tomorrow, so I'm 2-4 is available. Okay, 2-4 and Math Excel is available. We'll make it due on Monday. Because I'm not going to be here tomorrow. I'll be here in the morning to do the retake if you want to take the retake. But I have to leave and go to a professional day at Rhodes. Okay, so I have to do work out there tomorrow. So 2-4 will be due on Monday, so you can ask questions Monday in class before it's graded. But tomorrow in class, there will be an assignment that is due at the end of class. Okay? When I'm absent, I don't like to just give you basically 45 minutes to do whatever you want to do. Okay? Because in the past I'd give an assignment and be due the next day I get back or the next day we have school, and nobody used that 45 minutes appropriately, and then they were watching YouTube or whatever. So tomorrow it'll be assignment. It'll be in class. If I'm using an in class 45 minutes, that assignment's going to be weighted a little bit heavier than a normal homework assignment. Does that make sense? Okay, because I'm using 45 minutes of instructional seat time. So it's going to be a little bit of maybe a 20-point assignment instead of a 10-point assignment, something like that. Okay, but that'll be due. It's not going to be anything that blows your mind, but that will be due tomorrow at 3:15. Okay.